Good day, Bayaw. Today, we have here another problem from the book of Thermodynamics by Singal, Chapter 5, the second law of thermodynamics. A 50 kilogram iron block and a 20 kilogram copper block, both initially at 80 degrees Celsius, are dropped into a lake at 15 degrees Celsius. Thermal equilibrium established after a while as a result of heat transfer between the blocks and the lake water. Determine the total entropy change for this process. First, we will be identifying our given. We have here the mass of the iron block, that is 50 kilograms, the mass of the copper block that is equal to 20 kilograms, the temperature of both of the blocks that is equal to 80 degrees Celsius, the temperature of the lake that is in 15 degrees Celsius, and we will be solving for the total entropy change of the system. Here is our solution. We have here the equation of the change of entropy, that is equal to mass times the specific entropy of state 1 minus specific entropy at state 2. This equation is also equivalent to the constant pressure of specific heat times the natural log of temperature at state 2 divided by temperature at state 1. And we have the equation of the change of entropy, that is mass times the constant pressure of the specific heat times the natural log of temperature 2 divided by temperature 1. So we will be plugging in our values. First is in the iron block, that is equal to 50 kilograms times 0.45 kilojoules per kilogram Kelvin times the natural log of 15 degrees Celsius plus 273 Kelvin divided by 80 degrees Celsius plus 273 Kelvin. And we have the change of entropy in iron block that is equal to negative 4.579 kilojoules per Kelvin. Next is the copper block, that is equal to 20 kilograms times 0.386 kilojoules per kilogram Kelvin times the natural log of 15 degrees Celsius plus 273 Kelvin divided by 80 degrees Celsius plus 273 Kelvin, that is equal to negative 1.571 kilojoules per Kelvin. Here, we have the energy input minus energy output is equal to the change of energy of the system. And since we don't have work, kinetic, and potential energy here, we don't put them in our equation. So we have the heat output is equal to the change of internal energy. So that is also equal to change of internal energy of the iron block plus the change of internal energy of the copper block. This change of internal energy is also equivalent to the mass times the constant pressure of the specific heat times the change of temperature, that is T2 minus T1. So we have this final equation to solve for our heat output, that is the mass times the constant pressure of the specific heat times T2 minus T1 of the iron block plus the mass times the constant pressure times the T2 minus T1 of our copper block. So we will be plugging in our values. We have this 50 kilograms times 0.45 kilojoules per kilogram Kelvin times 353 minus 288 Kelvin plus 20 kilograms times 0.386 kilojoules per kilogram Kelvin times 353 minus 288 Kelvin. And we have this heat output of our blocks that is equal to 1964 kilojoules. To solve for the change in entropy of the lake, we have this equation, that is the heat input of our lake divided by the temperature of our lake. So a short explanation here, the heat input of our lake is equal to the heat output of our blocks. So that's why we have this value here, that the 1964 kilojoules divided by 15 degrees Celsius plus 273 Kelvin, and we have this, the change of entropy of our lake, that is equal to 6.820 kilojoules per Kelvin. So to find the total entropy change of our system, we have this equation that is equal to the change of entropy of our iron block plus the change of entropy of our copper block plus the change of entropy of our lake. So we will plug in our values. We have this negative 4.579 kilojoules per Kelvin minus 1.571 kilojoules per Kelvin plus 6.820 kilojoules per Kelvin, and we have this, the total entropy change of our system, that is equal to 0.670 kilojoules per Kelvin, and that is our final answer.